Okay, so let's go ahead and complete what we started last time, which was this factorization method. And I had come up to the point, right, where I think we had something like W is equal to, what was that, ms plus t? Is that what we had used? Yeah, m into s plus t. T had translations in it, and so you had something like f number of frames, right? So you had like, what is it, f number of frames? So you have like 2f cross the number of points is q, right? And m had 2 rows for every frame. Therefore, this must be like 2f cross and 3, right? Every row has 3 coordinates. It's actually a rotation. And this S had 3, and then there were, so this was a structure, right? So this had, what was it, 3 cross q, right? You had q scene points, and therefore this guy will be like 2f cross q. And this was a measurement, which meant that along a column you had a correspondence across f frames where you had x and y coordinates, and you had q such columns, right? That was the understanding. Now let us actually define a w tilde. Okay, first of all, before that, what will be the rank of w? I mean, what can it be? Rank of w less than or equal. Of course, we can't say what is the actual rank. What will it be like, less than or equal to? What can be the rank of S m maximum? 3. What can be the rank of S? 3. Okay, what can be the rank of m into S? No. How do you find that? I mean, if I have 2 matrices A into A dot B, what is rank of A dot B in terms of the ranks, individual ranks of A and B? It is minimum of rank A comma rank B. Okay, so we don't know. I mean, S we are saying is less than or equal to 3. Rank of M is less than or equal to 3, but which one is smaller and all we do not know. So, and T has a rank. Rank is 1. It was the same column getting repeated, no? Can you guys not recollect? What was it like? T1, 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 right? T21, T21, T21. It was just the same column getting repeated. So the rank of T is actually less than or equal to 1. Okay, therefore rank of W, what is the rank of A plus B? Less than or equal to rank of A plus rank of B. Therefore, rank of W is less than or equal to 4. Okay, rank of T is less than or equal to 1, rank of M into S is less than or equal to 3, and therefore rank of W can be less than or equal to 4. But now, right, we are going to actually nullify the translation and make it rank 3. So how we do that is, let us actually define a W tilde, which is, let's say, W into, what do we do? I think we do something like I, an identity which is Q cross Q minus 1 by Q all ones. This is also a Q cross Q matrix, of course. What does this do? If you do a matrix like this, right, what does it mean? What is the action of a matrix like this? I, all diagonals, ones and all along the diagonal, and then 1, 1, 1 along a row, and I am not doing Q square. You could notice that I am doing 1 by Q. When do you do this? I mean, you must. No. I mean, let's not go into signal processing and all. You have a data, and this is called data centering. Right? This is like, yeah, we are removing the mean, right? Just mean centering, right? Mean centered. So all that this will do is this will give you a mean centered sort of say W. Mean centered W is actually W tilde. Okay, now you replace W by W tilde, W by MS plus T. Right? That is coming from here, and then you have the same guy I Q cross Q minus 1 by Q blah blah. This ones all ones, guys. So now if you expand this, right, this will be like MS, and all these dimensions all will match. Okay, there is no problem. I Q cross Q minus 1 by Q plus T. T is a matrix, by the way. This is not a translational vector. Minus 1 by Q. So what will be the second term? What will be the second term? Second term is actually 0. Not because I minus 1 by Q is 0, not because of that, but then because T is all the same column repeated. If you look at the entries of T, right, it was like T11, 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 the first row. Then next was what? T21, T21, T21. So if you do mean is T11 itself, right? So if you do that, you will get all entries 0. So every entry, right? So the mean centered means every entry is subtracted from the actually mean value of that row. So mean centered means what? I mean every element of, so let me write this down, right? I mean if you have still not gotten it, every element of W is subtracted, no, not subtracted, I mean from every element of W, the other way around, otherwise you will get a minus sign. From every element of W, you subtract the mean of the row, of that row. You subtract the mean value of that row. Okay. So in this case, right, you can, as you can imagine, the mean is the same as every element. It's all T11, T11, T1. Therefore, this goes to 0 because of the nature of this is going to a 0 matrix of whatever size, right? What will be its size now? 2f cross q. Okay, doesn't matter, it's anyway 0. So due to the nature of T, not because of anything else, due to the nature of T, T being, right, what it is. And therefore, and now this one, okay, this is like what? S into I q cross q minus 1 way, that's like mean centered structure now, right? Whatever we did for W tilde, now we are doing it, it's just invariably it's coming and sitting on S now. Therefore, this we can write as M into, let's say, S hat, where I absorb this IQQ into S. Okay, and therefore, this I call as mean centered structure. So I have W tilde, right, is equal to this. Now, if you look at the size of M, it is 2f cross 3 and S hat is 3 cross q. Okay. Now, as always, right, we would want to sort of look at the SVD now of we say W tilde. W tilde, right, if you do an SVD, right, first of all, what is M into S hat? So we just know, so M has how many? This one 2f, right? 2f cross 3, right? Because each row is 3 cross 1 and S is like 3 cross q, right? This is what you have, no, S hat. Now, if you do an SVD, right? So W tilde will be like U diagonal V transpose, where this will be 2f cross 2f. This will be 2f cross q and V will be q cross q. So that this becomes 2f cross q, right? That's how it will be, no? But no, but then the point is, okay, what is the rank of this guy? A rank of W tilde. See, if you notice, rank of W was less than or equal to 4, but that had a translational component sitting, whose rank was itself less than or equal to 1. So W tilde has nullified the translation also. Therefore, this will be, right, minimum of the rank of W, comma, rank of S hat, right. So rank of S hat can be a max of 3, rank of M can be a max of 3, and therefore rank of W hat cannot exceed 3, right. I mean, why we are interested in this? Because this D, what is the point in having a D that is that big, right, when the rank of W tilde is only can at most be 3, correct. So now what you can do is you can actually simplify this, right. I mean, you don't have to have such a kind of complicated big D, right, when actually hardly rank of W tilde is like less than or equal to 3. Therefore, right, what you can do is, so you can actually pick the, so what would you do, right? So you pick the first, I mean, let's kind of say define something like define, what are we defining? Okay, U dash, okay, U dash to be the first 3 columns of U, and all this is assumed to be arranged, okay, right, I mean, arranged in the order that you have a largest singular value down to the smallest and so on, all that we are assuming. So, right, define U had to be the first 3 columns of U, then take D hat to be a principal 3 cross 3 block, 3 cross 3 block of D, and V dash whatever, right, let's say what is it, the notation that I am using is, okay, V dash transpose to be, you can either say the I mean 3 rows of V transpose or right equivalently 3 columns of V, right. Let's say in terms of column to be the first 3 columns of V, right. And therefore, what you can do is you can effectively write W tilde, which is actually 2f cross q, we can write this as u dash, not u dash, I mean yeah, u dash, right. It is not a transpose, by the way, it is just some other matrix, okay. U dash whose size is 2f cross 3 now, and d dash is 3 cross 3, and your v dash transpose, right, as we are writing, is 3 cross q, okay. And this you can further kind of split as u dash root d dash root d dash, I mean root d dash, you know, right, it's just a matter of taking the square root of all the diagonal values, v dash transpose, okay. And therefore, this you can call as m tilde, and this you can call as your see s tilde if you wish, right. And therefore, right, what you have kind of right effectively achieved is you have I mean you have the observations with you, which are the feature correspondences coming from across whatever f frames, oh sorry, yeah, f frames, and there are q scene points, and this observations, right, that you have, I mean for let us say in this matrix W tilde, you are able to split it up into, decompose into actually rotations, which is what m tilde contains, rotations, and then the scene structure, right, which is built in this S tilde, right. This has the 3D scene in it, right. That has like x1, y1, z1, all the way up to q, right, xq, yq, zq, and that is what you have done. And you will still be probably interested in the translations also, because you need the pose, right. After all, you are solving for the pose, you need rotations as well as translation. So the simplest thing to do is get back your what do you say, right, get back your say S tilde. So you have your I mean you have this mean subtracted thing here, no, that I showed earlier. So just go back there, right. So where was this mean subtracted thing? Okay, so yeah, so from here, right, you have your S hat, which is S into this mean subtracted. So you can actually get your S, and once you have your S, you have your M, and therefore, right, all that you need to do is you need to take your I mean you have your see, original W, right. So translations, okay, get S from S hat is easy, because it is just that I minus that operation, and just take it onto the other side. Then translation is simply the original matrix W minus what you call MS. That is it, right. So you have your translations, you have your say rotations, and you have your 3D scene. Okay, this is called the factorization method, and still the point is, right, this is not the final call, right, in the sense that one, of course, we assumed that that the model is orthographic, which was a simplification that we made, but the whole point was to convey how this is done. I mean, you could have done with actually this one a perspective sort of a projection model, but that would have been more involved. I thought it's good to sort of look at something that's kind of more easy to understand. And of course, right, this is what is also normally taught. Okay, this orthogonal projection model is what people typically use, and now you know how this is done. But then, right, it doesn't mean that right, you have sort of a dense 3D reconstruction, right. You don't have. You still have only a few points, right, for which you have the sparse feature correspondences. You have a 3D 3D points for that, and then the key thing is you have the poses now, but even the poses need not be accurate, right, because one of the things that we were assuming here is that our correspondences are all noise free and all, which will not be the case, right. It can either have noise or it could be outright wrong, right, both can happen. So what is normally done is these are all taken as initial estimates only. Okay, so you can actually use a DLT, what is called a direct linear transform, which is the other route, right, which is to kind of compute the fundamental matrix, then compute the essential matrix, then from the say right essential matrix you can go back and find your what do you call R and T, right, from the essential matrix. Then you can actually triangulate, and then you can scale your component, right, as you go from one pair to another. So there are various ways in which you can arrive at the initial estimates. But what is typically done in a kind of structure from motion is that whatever initial estimates you have, those are still considered as initial estimates. But the real thing that happens is what is called a bundle adjustment. Okay, this is where all the right errors and all are actually accounted for, because your correspondences need not be perfect. there could be noise in the way you have located the correspondences, there could be outliers in the sense that you have probably matched things wrongly, because you are just depending on something which is just something like a SIFT or SURF, right, which is actually giving you the feature correspondences.